University. And prior to joining Georgetown, he spent 2 years as a research scientist at Yahoo Labs in New York. And before that, he received his PhD for the theory of computation group at Harvard and was a research fellow at the Simons Institute for the Theory of Computing. And his research interests include, besides zero-knowledge proofs, quantum computing, learning theory, complexity, and algorithms. And I want to add that Justin is, I mean, you carry around different papers in your head. And one of the papers I found really nice is, and carry around in my head is Justin's paper from 2013, where he, building on the GKA framework, gave some really nice and efficient proof systems for low depth circuits with n log n time and in special cases in data parallel computation, actually the linear time. So if you want to read what I think is one of the nice and classical papers in this field, then go have a look at his paper. Daniel is the lead cryptographer at Kedit, a company that you probably very familiar with since they're deeply involved with the ZKProof workshops and develop privacy enhancing technology. He graduated from the Weizmann Institute with a master's degree in applied mathematics and computer science under the guidance of Zwiga-Rakersky. And he's also, of course, the ZKProof hero who's really driven forward ZKProof and promoted this workshop through all the years. So before I give it over to the word over to Daniel and Justin, let's just remind us that we would like to have a note taker. So if anybody will volunteer for this session here, then please do. Excellent, thank you, Mary, for volunteering to take notes. And the format of this is a 30-minute presentation, and then we'll have a 60-minute discussion on topics. And remember, this is actually a standards proposal, how we want to benchmark zero-knowledge proofs. So the discussion will be aimed both at technical questions to the presentation, but also how we can turn this into a standards proposal. So please go ahead, Daniel and Justin.
Thank you, Jens. Let me share my screen. Make this. Of course, as soon as I'm sharing my screen, I can't find the presenter view. Oh, here it is. Okay, so I think this is ready to go. Yeah, thanks, Jens, for the introduction. So this, I assume everyone can hear me. Okay, I'm just assuming. Okay, great, all right. So this talk, as the title suggests, is about a benchmarking framework for zero-knowledge proof systems. So let me start by saying why we might want to develop a benchmarking framework. So, you know, the situation with zero-knowledge proofs these days is there are a huge number of schemes. Many of them are designed with different applications in mind. So no one of them is best. No one dominates all the others. And this may be an inherent situation that will persist indefinitely. It might just be the case that some cost trade-offs are inherent in any zero-knowledge proof system. And, you know, there's never going to be one scheme to rule them all. And moreover, like, innovation is constant. So there's, of course, a flood of new protocols and new tweaks to protocols coming out on a regular basis. So it's a lot to keep track of. And, you know, since no one protocol is best, we have to be able to compare all of them. And you might think, okay, so we'll do that. So we'll come up with some kind of apples to apples method for comparing every pair of protocols, or in an absolute sense, evaluating each individual protocol. You know, problem solved. And in fact, it's much more complicated than that. And I'd go so far as to say the notion of an apples to apples comparison is essentially an impossible ideal. So we'll go into great detail about the many complications in benchmarking throughout this talk, but just to mention a couple up front. So for any given proof system, there are well over a dozen costs or properties that may be extremely important in any particular application. And when people do go and evaluate their proof systems, they tend to focus on the costs that are most important in their mind or for their application. And they might not report the entire trade-off space or costs of the protocols. And even with good faith efforts from everybody, this is a very complicated thing to do. And in general, the situation these days, I think, is if you're somebody who wants to use a zero knowledge proof in some application, you might understand the cost of your application very well, but even then it's very hard to know like which kind of deployed, maybe open source proof system is going to be the best one for you to use. It's just a very difficult, complicated space out there. So yeah, evaluating these proof systems is subtle, right? So the two main issues that make it so subtle and complicated, as I've already mentioned, complicated trade-offs and costs. So any given proof system, there could be several, let's say 4 knobs you can turn for a proof system, which already means that kind of the trade-off space is 4-dimensional, because any setting of the 4 knobs is going to result in different costs. But then if there are over a dozen costs that you care about, that means that the benchmarker is trying to map out a 4-dimensional subspace of at least a 12-dimensional kind of underlying space. So just painting a picture of these trade-offs is not simple. And moreover, performance, it depends on a lot of things, and very, very heavily on a lot of things. So different proof systems have different modes of operation in terms of some of them are able to or need to amortize costs over whether a batch of inputs or kind of indefinitely over verifying the same computation on many different inputs. The cost of any proof system might vary a lot by the type of statement being proven or the size of a statement. A proof system might be the fastest on small statement sizes, but be very memory hungry and therefore unable to, totally useless once the statement size gets bigger. Different proof systems have undergone different efforts at optimizing them. So if you're comparing a proof system that the entire community has spent years optimizing already to a new proof system where maybe one group has done their best to optimize it, that still can make a huge difference. So this end state of affairs is that this is a significant barrier to development and continued adoption of zero knowledge proof systems, just because it's hard even for experts, much less newcomers to the area, to evaluate progress or to identify the best proof system to use in whatever application they have in mind. So, the area is healthy, there's continuous innovation and so forth, but it certainly would be healthier, and I think it'd be easier to adopt these protocols if we were able to address some of these challenges. So the goals of this proposal there are 4 of them, and I think the first 3 are reasonably straightforward. So we want to carefully enumerate these challenges and subtleties that I've already described several of, and we want to articulate best practices to address them. Now, the current community reference document has some discussion of this, but it's a little bit abbreviated, so you can just think of these 2 goals as trying to be more thorough and careful in terms of expanding that discussion. We also want to at least discuss possible tooling to help people in this difficult task of benchmarking. Most of the tooling is future work to implement, but we'd like to at least start a discussion about it. And then the 4th goal is kind of the key goal to discuss. So we think about putting forward a concrete framework by which I mean essentially a small list of quote representative functionalities to test proof systems on. And kind of a recipe for everyone to follow if they're benchmarking a new proof system. And particularly in regard to this 4th goal, I think that it should be a little bit controversial whether this is even a good thing to try to do. And I actually don't think there's full agreement amongst the authors of this proposal whether this is a good thing to do, because it has the potential to do harm. So the main concerns are to avoid stifling innovation and to avoid biases. So by which I mean, in terms of stifling innovation, if a benchmark functionality kind of by design has inherent in it a certain paradigm for developing a proof system, then you're already kind of forcing protocol designers into a box that they may not have to be in. So even to kind of run the benchmark, they might not be able to innovate in certain ways. For example, if you tell them they have to work in this kind of front end plus back end paradigm where first you generate a circuit or an R1 CS constraint system, you're already forcing them into a paradigm that maybe in the future we'll be able to avoid. And secondly, we don't want the benchmarks to kind of inadvertently favor some approaches over others in ways that are not actually reflective of actual costs and so forth. Kind of any particular framework might accidentally be favoring certain costs over others. Okay, so to get into a little more detail about challenges and how we propose to approach them, I wanted to briefly list some of these more than a dozen properties of any proof system we would want people to measure and report. So the quantitative costs that people can definitely measure, like report a number for, include prover time and space, verifier time and space, the size of the proof, the size of public keys, and reference strings and so forth. And then there's the security level, and of course, security comes in multiple flavors. There's statistical security, which kind of says no matter how hard a prover works to try to trick the verifier or break zero knowledge, it's just not going to have a very good probability to do that. But then there's computational security, which says, well, if the prover were able to run for 1 billion years, they would be able to, trick the verifier with decent probability, and it's really just computational limitations that are preventing bad behavior. And then there are additional qualitative properties, that you can't necessarily measure. So what cryptographic assumptions the protocol security is based on, is it post-quantum secure? Setup assumptions, meaning is there a structured reference string, that some kind of trusted party has to generate? If there is it universal, meaning one setup works for any computation of a given size you might want to run? Or do you have to pay that cost every time you care about a new computation? The same statistical versus computational security distinction applies also to the zero knowledge. And then there are these properties that are maybe even less obvious, like the simpler the protocol is, the more likely you might be able to formally verify its correctness or formally verify that an implementation correctly implements the theory. And of course, it's natural, we've seen some implementations have security flaws in them, and this seems more likely kind of the more complicated the protocol is. So all these properties people care about, of course, it's very difficult as a result to compare proof systems. So we're going to elaborate further on some of these challenges as we go. On this slide, we kind of try to identify 4 boxes to organize our thoughts in terms of where the challenges lie. So I'm going to start with the maybe the most concerning challenge of all, which is just, is it even possible or reasonable to try to identify a small set of, quote, representative functionalities on which we're going to ask people to focus their benchmarks on. So yeah, there are many issues in trying to do this, and I've mentioned some of them, but I'll elaborate now. So there is essentially an infinite array of functionalities people might care about, and qualitatively they vary very widely. So there are cryptographic functionalities, just as an example, proving knowledge of the pre-image of a collision-resistant hash function. So this is a kind of a primitive people want to use in more complicated cryptographic protocols all the time. And then there are totally different things people care about, like say, some authority has committed to some data set and signed it, and later wants to prove that it ran some analysis on that data set. So now you're applying the zero knowledge proof to some arbitrary data analysis of some large data set. And this looks nothing like proving knowledge of the pre-image of a hash function. And of course, the size of the computation of the statement that you're proving is totally different. And as I did mention earlier in the talk, there's lots of avenues for innovation. We don't want to put people in boxes that they don't need to be in and kind of inadvertently prescribe some design paradigm that later someone realizes, there's a totally different way to do things. I think I've already talked about the large trade-off space and the fact that speed on like a given fixed input size might not say anything about scalability, meaning how big a statement size you can get the system to run on before it's totally out of memory. And there's another subtlety, which Daniel will elaborate on soon, which is in certain applications, the data that you're kind of running the zero knowledge proof over has structure. And if you ignore the structure, you're going to potentially pay a large price in efficiency and cost. But how does a benchmark capture that structure when it's so application dependent? Right. So if the benchmark says, oh, you can assume the structure, then all of a sudden, the results of the benchmark are only useful for, the 1 or 2 applications that actually have that structure. Okay, so there are all these challenges. Let's just say we're going to fight through them anyway, and we are going to identify a small representative set of functionalities and tell people they should focus on benchmarking on them. I think we can at least say the following. So if we focus on functionalities that are already useful in some existing applications, and in those applications are actually already a bottleneck cost, then at least we can say that by asking people to innovate on those particular applications, their innovations will be useful, and in fact, immediately useful, because we can just plug them in, the best protocols into the existing applications, and those applications will have their efficiency improved. But of course, we also want a diversity of these applications. For this reason, already mentioned that different proof systems can have wildly different costs depending on the kinds of statements they're being applied to. So I wanted to just highlight one more issue, and then Daniel's going to take it from here, which is designer flexibility. So to introduce this issue by example, suppose we did declare we're interested in this functionality of proving knowledge of pre-image of a cryptographic hash function. So so if we want the, sorry for the distraction. If we want the protocol designer, are we going to allow the protocol designer to choose the hash function? If the answer is yes, or if the answer is no, there's a kind of an entire can of worms opened up. Because if the answer is yes, so the protocol designer designs their own kind of snark-friendly hash function, there are questions about how you quantify security of the hash function. Have there been sufficient efforts devoted to trying to kind of break the hash function versus, if it's SHA-256, people have been trying to attack that for years. And then you run into issues where it's not clear where efficiency improvements are coming from. Is it coming from ingenuity in the hash function, in the proof system, or in their interaction? And lots more issues beyond that, but that's kind of the idea of the can of worms. Whereas if you say, no, we're going to tell the protocol designer what hash function they have to use, well, now you're no longer capturing the high level goal of just developing the most efficient protocol for the general functionality of identifying pre-images of hash functions. So Daniel is going to now describe a specific solution to this, which is kind of proposing to study each functionality at different levels of generality. So I'm going to hand it over to him.
Well, thank you very much, Justin. So I understand from Jens, I have about 10 minutes to go through the rest of the slides. So everybody can hear me well? Just making sure. Good. So just sort of to take back where Justin was at, we want to give an example of a representative example of what it would be sort of to go through a benchmarking functionality. So we've chosen sort of the example of set membership. And what you can see from this sort of diagram, you can see the full diagram, right? Okay. So what you can see from this diagram is the different branches sort of represent different levels, right? So we think that, for example, the top level is sort of to give this high level functionality. Okay, you need to prove set membership, right? Up to you how you do it, how you're going to prove it, what the primitives you're going to use, what the underlying elliptic curves you're going to use, even what representation of the encoding language, right? So the specific IR language. The next level, let's say we are actually going to fix, the specific functionality. We're going to instantiate this functionality itself, right? So either Merkle trees or RSA accumulators and so on. The next level, okay, now we need to actually fix the sub-functionalities, right? So we call these levels the intermediate levels, and we'll see that in a second. what if we fix the SHA-256 function, right? So, okay, so do we implement it in a Boolean circuit or do we implement it in our R1CS, right? For example, of course, these have different trade-offs, as Justin was also saying before. This encompasses sort of the intermediate levels where we instantiate the functionalities, and then we sort of fix the specific IR, but still not fix the implementation of the statement in that IR, right? So we still sort of allow for a component of optimization there. And then the final level, which is it's actually missing here, but you can imagine we give a fixed file, right? That it's sort of, you need to just run this as input into the proving system. In the given language. And of course, you can expect that there are going to be some branch outs for bit security and for potentially statement size for thinking about the trade-off there of, some proving systems may be better for smaller statements and so on. In the Merkle tree example, it could be the depth of the Merkle tree and things like this. So just to make it a bit more specific, like the high level, the highest level that we were imagining, as we said, is the functionality. And ideally, we would like to start from an ideal functionality. And what is actually fixed here are the security requirements associated to the ideal functionality, right? Here, basically, the designer of the protocol, right, or the one that is benchmarking, can optimize for the statement itself for the proof machinery. He has the full spectrum of design flexibility. In the intermediate levels, as we were saying, here's where we instantiate the functionality. As we saw in the previous example, like there can be several intermediate levels, right? If we only talk about, for example, the pre-image of a hash function, well, maybe there is only one intermediate level because you're only instantiating one functionality. Here we're allowing somehow to optimize for the front end, but specifically around the encoding method, right? So we didn't fix the IR and we didn't fix the specific implementation of the statement. And of course, we also, at every level, we optimize for the proof machinery itself, right? But that's sort of clear. The next level, this lower IR, again, we fix the specific IR. And now we're sort of optimizing for the specific implementation in that intermediate representation, right? And you kind of get the gist of it. The final bottom level is sort of this file format that I'm just giving you as a way to input it into the proving system. But of course, we need to be wary of this sort of framework. And, first of all, we need to understand, what are the different ways that overfitting could take place. So, for example, we would like to sort of prevent people, or maybe not prevent, but be wary that some people may be optimizing for the specific functionalities in the benchmark, right? And maybe this is not a bad thing as long as the framework itself sort of identifies that this is exactly the purpose, right? So if someone is really good at one specific level but very bad at another one, well, that sort of should say something about what they're trying to do for overfitting or what the goal of sort of the trade-offs that they're taking. And of course, we want to be wary also to sort of inflate the importance of the bottom level, given that it's sort of for more specific comparisons, maybe narrowed comparisons, but it's still important. And the same applies to all the other levels. Like one question that we want to raise later for discussion is, what are the more important or less important levels? And if at all there are any levels that are more important in some sense, right, for comparing. And we also say that because, thinking about how to distribute these benchmark in some sense, we can allow for people to better understand the efficiencies and inefficiencies of their scheme. These benchmark could reveal a lot more about the source of each of these. Other considerations is that we may not want to have too many branches so that we don't have to keep track of that many sort of profiles. And a question for everybody is, whether designers should be able to submit functionalities, right? At the end of the day, specifically in the file format setting. So if we have one branch of set membership that ends up in, the sapling R1CS file constraint system for Pedersen hashes, well, does someone else want to use a different sort of file, right? So that's one aspect of considerations. And another part of considerations is also what Justin was saying before, that some cryptographic functionalities may be part of a larger protocol or a larger application. And then there could be potentially like a conflict in the way that the data is structured. So the set membership benchmark may not assume any actual structure, whereas if you're thinking about, for example, using set membership in snarks for RAM execution to enforce memory consistency, maybe you need to consider now what is the underlying field, and if you have to start serializing the elements into bits, then you're going to have an overhead, right? And then the benchmark is not going to be exact. So these are things that we want to keep in mind. And this is part of the question for the discussion, is if the structure is highly application dependent, what should we do here, right? Good. So we go to the third of the challenges in building this framework, which is around measurement and accounting, right? So here, what we know is that the literature is sort of rife with ambiguity. There's a lot of different trade-offs that are being presented, different comparisons in different machines. And I mean, it becomes a bit confusing even. A lot of tables. And one of the things that is important is to understand, and it seems to lag from some of the literature, that to understand exactly what counts in the benchmark that you're given, right? So, for example, for the verifier timer space, are you including the CRS generation? Are you including some of the input processing, the reading of the CRS, or only the proof verification, right? I mean, this is important to keep in mind. Similarly, for the prover time, does the witness reduction come into the prover, or did you do that as part of a pre-processing? Are there any other pre-processings that you have to do, right? Some schemes don't have the CRS generation as much as they have to regenerate some sort of verification key at every proof instance, and so on. So this is important to keep in mind as part of the measurement and accounting. Another important challenge is the underlying environment. So as we know and we saw in the previous talk, conveniently, all hardware favors some operations over others, right? And this is important to keep in mind in terms of zero knowledge systems, especially because some zero knowledge schemes may be more apt or to be matched to hardware or other machines. And so what we believe is that at the minimum, it should be that implementations should be submitted in a portable and modifiable way. And then that way they could be tested in different environments. And another point to make is in terms of, for example, memory of the environment, that, some machines maybe with massive memory are sort of more forgiving to memory hungry backends, right? In the sense that if you're comparing two proving systems, one has a lot of memory requirement, but you're actually testing them in a very large memory machine. Well, maybe it may not be fair for the other scheme, given that actually it may perform better in a regular machine, right? In a home PC or something. So this is also important. And of course, there are many other issues with the environment, as well as benchmarking parallelization. So this is a very subtle issue, where we want to be at a place where this does not sort of affect the way we're benchmarking, but we still keep it in mind, right? Maybe as a qualitative cost. And one thing to keep in mind is that a proving system that is tested on a multi-threaded parallelization, well, it's actually not equivalent to test a proving system on a single-threaded, right? Even if proof system B is sort of not amenable to parallelization and can only be run in a single thread, well, let's run proof system A in a single thread and actually get that as a way of comparison, right? At least maybe for one of the levels, or have two benchmarks. This is up to discussion. But the minimum is that we believe that there should be at least one baseline of comparison, right, for the runtime. So this is around the challenges. We also believe that there's a discussion to be had around tooling and analysis. So, to facilitate the actual benchmarking of the proving systems. And, to start with, some of the ways for measurement, right? So running a benchmark should be pretty simple. It should be sort of, you input the command and some parameters, right? Maybe the parameters specify the specific level of the functionality and which functionality. Here we have some sort of initial sort of example, both for high-level and low-level functionalities. And of course, for reporting, in terms of measurement, for reporting, one thing to keep in mind is that maybe the reporting should be done sort of within the code itself, because of course implementers know better where sort of the function of the prover starts and finishes, right? And this goes back to what we were also saying before, that in terms of accounting, that it needs to be clear from the get-go what is included in this benchmark. And in terms of the reporting itself, maybe printing a simple readable statement, right? And in terms of the process and publication, we would like to have a curated list of test commands and functionalities that we believe as the community are representative. We would like to accumulate measurements into a global results file, aggregate results into tables and graphs, and of course, publish regularly on GitHub and ZKProof. This way we can sort of establish a common place, not only a framework, but a place to look at these benchmarks that is accepted, right? We still need to develop all of these tools. This was sort of a preliminary understanding of what we would like to see and do. So these are some of the discussion points. I guess we went through most of them. You know, how do we not stifle innovation? What are the representative functionalities that we would like to choose? How do we prevent or encourage, right, this dichotomy of designers to tailor solutions for specific functionalities? Yeah, so thank you very much, and we're happy to go into a discussion. I guess Eran and Aurel are also here, so you know, the four of us maybe answering your questions. Thanks.
Thank you. Okay, we'll open up the floor for questions and comments. So please speak up if you have any. There was one comment from Kostas in the chat, and I don't know, Kostas, if you would share that comment and get the opinion of the question.
I can do. Thank you, Jens. So yes, my question is, in the community reference, we do have a section, a chapter discussing what benchmarks are required to be run. So I guess this work is actually extending this. And my question is, because in this particular section, we have a raw list of primitives, we don't categorize them, right? We use SAT256, but we don't know what does this test. Okay, we know sites used broadly, but does it test for batching, for recursion, for memory, for what is it required? And my question is, if we had a better categorization there, maybe we can avoid duplicates. I mean, running two different things that they are actually testing the same functionality or very similar functionalities, or we probably are missing some benchmarks for some very important properties. I don't know. I haven't gone into a full scan of what we're offering there, but yeah, it might help because now you have some good properties of what we have to test. Maybe we need real examples of this. Okay, how do I test batching? How do I test recursion? Is it okay if I only have one single benchmark for recursion, or this particular one is very specific and it doesn't really reflect the reality? So that's a question in general.
So I don't know if maybe Eran, do you want to take it since you were also in the implementation?
Sure. First, yes, the proposal extends the benchmark sections of the community reference, and if this proposal is pursued, then we would replace the benchmarking section of the community reference with basically the abstract of this proposal. The question of which functionalities to include is definitely a delicate one. And there are also the considerations that Justin raised, as well as the issues of minimizing overlap and minimizing the total amount of the total size of the menu to not overwhelm implementers and readers. This is very much an open problem. We have some suggestions. We have inputs from others, including the prior work that was done on this, but definitely a big part of the concrete work that the working group for this proposal will have to do is to find a reasonably sized and well representative and indeed low overlap set of functionalities, and then formalize them, specify them at the multiple levels that Daniel described.
Maybe I can add. You go for it, Justin.
Okay. So, I mean, one possibility is, the community could decide that kind of a sensible approach is maybe to be a little less ambitious than saying, here's the representative set of functionalities that like everyone should focus on. I mean, I don't think we would ever get there because that truly in the sense that there'll always be other functionalities that people care about and that are important, no matter what small set you pick. So, it might make sense to just have kind of a delineation of all of the subtleties people should be aware of and a list of best practices. Stop there. Then there's some tooling that people are, it just hopefully helps people in measuring everything. And then there's like a set of suggested functionalities, but people are free to go arbitrarily far away from the suggested set as well. Yeah, it's just a. Yeah, I'll stop.
But my question, yes, I will continue. My question is, if I am creating a new, let's say, new ZKProof system, and I know it's good against batching, how do I test against other ZKProof systems only for the batching property? I want to advertise that I'm better at batching. What do I do?
So let me say something around recursion, because you also mentioned recursion as one of the examples, and I think recursion is interesting. Because recursion can be considered both sort of at the level of an application and at the level of sort of the fundamental mode of operation, if you wish, right? Like Halo, for example, we know it's better fundamentally at doing recursion than other schemes. And on the other hand, you have like Zexy, for example, that is also using recursion for applications. So in terms of categorization of functionalities, there is definitely sort of different ways to categorize where it's not clear how, but it will be important, as you say, to find a way to compare these properly.
I think, by the way, that new proof systems that recursion will be a feature that is common to lots of new proof systems, because it doesn't really prevent you from doing other optimizations. So it's natural to combine it with other things. It doesn't really restrict you very much in what other optimizations you can apply. So I suspect that a new batch of proof systems will basically, most of them will support recursion.
Specifically about batching and recursion, these kind of external properties. So there are two approaches here in terms of how we can integrate this into the benchmarking framework. One is to treat these as orthogonal and say, okay, we're going to do, say, set membership. How fast can you do that? Well, how fast can you do 1,000 of these? Okay, and just exercise batching. And then you can apply generically to any of the proposals as another dimension. The alternative is to just consider this part of the functionality and say, okay, the functionality of interest is proving 1,000 set memberships. You can do it at the highest tier of abstraction any way you want, maybe using batching, maybe using some very fancy accumulator that allows for this to be done in one shot rather than batching. And I think that this latter approach, doing this in a tailored way rather than as adding yet another dimension, it seems more flexible and it lets us focus on the really useful cases that practitioners care about. But this is definitely something that's up in the air.
So there's a potential pitfall here, which is that not all batching is equivalent. So there's batching of existing proofs that are generated independently, and then there's batching a whole set of things that at the same time, and those are not the same functionality.
I agree.
But so I guess there is another maybe a subdivision as well of like, is it sort of in parallel or in right all to one, right? So are you basically like batching one after the other, right? Or all in one? Is that sort of what you were saying? Like you're taking, yeah. I'm trying to understand exactly the point you were making.
suppose that you're batching a bunch of proofs and the zero knowledge proofs that require secret witnesses. Clearly, the only people who can make those proofs are the people who know the witnesses. And then you're in, say, a succinct blockchain situation, so you have to aggregate those proofs somehow. That's completely different to not specifying sort of where the witnesses come from and just saying that you have to end up with the result of proving all of these things.
Okay, yeah. Good point.
Any further questions along this specific line? Adrian, you had a question. Would you like to ask that question?
Basically, just from an implementation point of view, like I personally learn a lot better just by reading code and just trying to find implementations. Like if you're going to do a whole bunch of benchmarks, will we be able to access and learn from these published implementations, or how do you prove that you ran the benchmark correctly?
You should use a zero knowledge proof. No, I'm kidding. That's a very good question. I mean, you know, ideally the implementations would be open source, and then, you know, in every experiment you want it to be you know, replicable, right? You want to be able to sort of replicate the results.
So to do that, the hardware needs to be replicable as well. So something like standard AWS instances. I mean, you don't want to be too dependent on a particular cloud provider, but that's a pragmatic way of doing it.
Yeah,
absolutely,
so
absolutely.
In the proposal, we did kind of raise this possibility of, you know, trying to get, you know, quote, apples to apples comparisons, or by, you know, kind of designating like some specific cluster as, you know, like the environment everybody should test on or something. And, you know, we, in the proposal anyway, we said like we see problems with this, not just being dependent on one provider, but, you know, there's an administrative burden. And of course, people will ultimately be running these things, you know, in the wild on all sorts of hardware. So any particular machine is going to favor some things over others, just in a, you know, so it's something to think about, but there might be major, you know, the best we might be able to say is just like best practice, and a really important one is put out, you know, implementations that are easy to port and run and modify, and that's the best we can say. It's a possibility.
Yeah, I do think actually that standardized hardware platforms are useful, but that they shouldn't be required. You need the portability anyway. I also made a comment on the chats that we should definitely include multi-threaded performance, because you can't infer multi-threaded performance from single-threaded performance. So the difficulty there is that if you're looking at a new proving system, for example, then multi-threaded performance is not necessarily going to be optimized first. So that might be misleading, but it's better to have that information than not to have it.
Yeah, so maybe that's also why a single, like a baseline for single-threaded should be established, and then sort of build on that for multi-threaded.
On the other hand, where I know that my users are basically going to be using 4 threads or 8 threads, so is single-threaded performance actually that relevant to me?
Right. So I think the issue is that, you know, there's huge variation with most proof systems in terms of the effort that's been devoted to parallelizing them so far, and, you know, what parallel architectures they have been, kind of the effort has been devoted to. So it basically becomes, in some sense, it's impossible to compare. And I don't mean we absolutely should try to compare. It's just subtle and difficult. So the one thing we can say as a baseline, you know, where these issues don't arise is, you know, just report the single-threaded things. It might be essentially meaningless, but at least it's you don't run into the whole can of worms from the start.
But I mean, except for embedded applications, who buys single processors anymore? Even mobile phones have 4 or 8 processors. No one buys a PC with less than 4 or 8 processors.
I think what you're saying is compatible. Basically,
Yeah,
for
but
every
even though
such
you wouldn't...
option, we have the decision to make. Do we standardize a specific thing that is well-defined and comparable between implementations and between machines and so forth? Or do we just tell people what to report about and hope that they do a diligent job? And for something as finicky as multi-threaded configurations, which can differ literally by the phase of the moon because it changes the temperature of your the CPU and therefore affects the overclocking, I think it's reasonable to, for now, just require people to report reasonably well and provide the source code so others can replicate on their own machines, doing fair comparisons to other implementations.
And couldn't we? Sorry, Dara.
Mary Mallow was interrupted.
Oh, right. Oh, yeah, actually, Mary was commenting. Sorry.
Oh, sorry. I was actually thinking that when it comes to single-threaded things, the aim here is not to say that this is the final implementation which we will port out to our customers, user base, whatever, and have them running. The aim is to use that when you are comparing against other systems.
Well,
so it is representative for a comparison.
If single-threaded performance was representative of multi-threaded performance, then that would be valid, but it kind of isn't. There can be a I don't know, several times difference when they run multi-threaded for things that have the same single-threaded performance.
Can we agree that if we can just find a reasonably well-specified, moderately multi-threaded configuration, then we can include that in addition to single-threaded?
Yes.
Well, actually, I do have a question though, like in relationship to the machine, like the infrastructure on which the algorithms would be run. Like, do we actually need such access to an infrastructure? I mean, I do understand that we have like a myriad of proof systems and both have their pros and cons and so on. But by just looking at like the constraint systems and by looking at the nature of the algorithm, we should be able to do some fair comparison upstream without needing to run anything. So if we take like a set of functionalities we'd like to evaluate, say MIMC, Peterson hashes, Shelat F6, or something like that, we may be able to pick the proof systems. So we take Groth 16, we express them in R1CS, and we all try to do some sort of crazy optimizations as much as we can. Like some other people try and do the same thing with Plonk arithmetization and so on and so forth. And by looking at the number of constraints, and also looking at of course the FFTs we're going to be using, whether it's Radix 2 and so on, we should be able to look at the algorithms themselves, and we know their complexity. So out of this, we should be able to do a lot of work upstream without needing to do anything.
So I think that is useful because that gives you strictly more information if you want to apply it to different platforms without actually running things. But it shouldn't be specific to R1CS, first of all. But I think just counting the number of multi-X and the size of multi-X and FFTs and things like that is a useful performance measure.
Yeah, I mean, it was not to be specific to R1CS. I mean, R1CS can be used for Groth 16, Plonk arithmetization can be used for Plonk, and other type of arithmetization can be used, like for instance, for bulletproof and stuff like Halo and so on. So you can use whatever arithmetization fits your proof system, and then by reasoning about the like underlying operations which are happening in the back end, we should be able to have some complexity which should tell us which algorithm performs strictly better than the other.
I mean, one thing you have to be careful there is that a gate is not the same thing between R1CS or Plonk or whatever. So you can't just have a single number for the size of the circuit and compare across different.
So one question I have is, sorry. One question I had is, how modular are these things, or do you have to build an entire proof system to benchmark what you have to say?
I guess what.
So to the extent that proof systems are modular, so for example, you could benchmark a polynomial commitment scheme. That benchmark will be valid for any proof system using that scheme.
So,
Right.
so I guess the follow-up question is, should we then build a collection of benchmarks for primitives that you use to build zero-knowledge proofs? I mean, I guess you could also imagine having benchmarks for, you know, how fast is an exponentiation and things like that, right? And then use that as a basis for theoretical calculations.
I mean,
so in some sense, we're saying like,
useful.
yeah, we're saying now that like on the one hand, we have the functionality, the levels of functionalities sort of on the one end, and then we would have like the levels of specificity of the backend systems, right? And I guess Yuval has done sort of the work for us to separate the information theoretic from the cryptography. And that's more and more being represented in papers today and could be pointed out. The thing that I'm worried about around that is that usually, or I don't know if usually, but, and again, I don't know all the libraries, but it seems like when there is implementation of a proving system, the, well, okay, maybe extra work would need to be done to refactor some of those primitives being used for the proving system.
That's definitely true, because there's not just one definition of a polynomial commitment scheme, for example. It depends whether it has zero knowledge, whether it has homomorphic properties, whether it's actually applicable to another scheme.
And just to be explicit, this actually addresses a different audience. Those who care about the bottom line performance, most importantly, the practitioners making a choice, would normally not care a lot about the ingredients and how they contribute to the time and memory complexity. Whereas the researchers who are trying to improve and find what to focus on would very much care, but is this dominated by the multi-export, the FFT or so forth? And can we plug in a better one? We actually have a discussion of this in the proposal. Right now, just in terms of prioritization, we think that focusing on the wall clock performance, the bottom line for practitioners, seems more important in terms of impact and usefulness. But if people are interested in pursuing the other direction of defining higher level metrics for things like FFT of a given size over a given field and so forth, that can definitely be added to the scope.
So there's kind of an intermediate position between those where you measure wall clock performance, but you break it down into how much of that is contributed by each component, and the proof system designer would, or the whatever you're benchmarking, would have to break it down in a sensible way.
This is very interesting. It sounds like a great approach. It would require adaptations to the tooling, which so far we've been thinking of as doing a black box external measurement of resources. Yeah. This would require some profiling information to be provided from within the implementation.
So in the presentation, you mentioned that the code under test would basically say when it was starting and finishing. So it seems not that more complicated to get it to log different steps within the process.
Yeah. Given a common language between the two for reporting things, yes, I think this is a great direction. It's relatively low-hanging fruit and will go a long way towards addressing the question of the cost of the underlying primitives.
One thing I will mention briefly, I don't know if it's obvious, probably is, but just in case. When we talk about, there's this discussion of kind of counting kind of abstract operations, you know, how many exponentiations and so forth, as an alternative or a way of dealing with differences in hardware and everything. One complication there is the cost of like a field multiplication or, you know, any kind of group operation is so dependent on the field or the group you're working in. And people use so many different fields and groups and stuff that you can run into issues. I mean, I know like some of the implementations out there, everyone's using the same group and so forth, but in the research literature, there's much more variation potentially. So just something to keep in mind. It's a potentially problematic thing with counting abstract operations.
Yeah, I agree with that. But it's just very complicated. Like I've also tried to think about this myself. Like there's so many moving pieces, even like in terms of languages. There's like libraries written in Rust, like a big part of them are written in Rust today. It's like a trend, but a lot of code is still written in C and C++. There's new libraries written in Go. And like these programming languages intrinsically do not have the same performances. So like in terms of benchmarking, we would also need to correct the results to take the different performances of this language into consideration and to have something which is like to actually compare apples with apples, because of course an implementation in Go will likely be slower than an implementation in C or Rust. So yeah, I definitely get the point. It was just like another sort of like tool to be able to try and compare the systems.
Yeah, I agree entirely.
I mean, if the interface between the code under test and and the benchmarking is just outputting a file, then you can do that from any language. I think we just have to keep that interface as simple as possible.
How would you do that, Dara? Sorry, I'm not sure I understood.
So as I understood it, the proposal was to just have the program under test write out a text file with the benchmarking results, basically. And that's not language specific at all.
I think the point was just that run like wall clock times.
Yeah, of course, yeah.
Yep.
So we're moving towards the end. So I just want to ask you guys whether there are specific things that we did not discuss yet that you think is important that we have a discussion about.
Actually, I guess the most important thing in terms of making this workgroup be successful is encouraging participation. We need people to weigh in on what cases are important to them along all of the numerous dimensions we've discussed. To the extent that we are going to provide concrete constraint systems for people to implement at the lowest level, we would need people to contribute such examples, preferably using a format we could all agree on, like ZK interface. And we have the work group on the forum. If you're interested in any aspect of what was just discussed, please join the work group and let's get something done there.
Cool.
Yeah, go for it there. Was anyone going to say anything? Okay. Yeah, to second the run, but also sort of maybe more concretely, like what do people think we should be focusing to start with? So we had this idea of having the levels on the front end side for the statement, the levels on the back end side. So I mean, I think starting with the suggestion of the proposal to sort of go first with the actual statement and sort of subdivide that into maybe some levels, right? Start with some maybe the most common functionality, which probably is like commitments or hash function. Maybe in coordination with the snark-friendly primitives working group to get something that is, you know, already an example and allow people, right? Because in some sense there is, right, yes, we need a representative set of functionalities for all kinds of applications on, but maybe right now one sort of functionality can be enough to start a more formal and proper comparison than what exists out there.
So some of the functionalities are just going to be repeat this primitive n times. And that's kind of easy because you just take all the primitives that the snark-friendly working group defined and just have one more parameter n. But then you have things like set membership, maybe other things. I can't think of anything off the top of my head that don't fit that pattern.
Well, recursion is one of them, right? Recursion is also a difficult one to do. Is it a one-level recursion, a many-level, etc.? And I wanted to say one thing, maybe I didn't mention it during the presentation. Also, in the highest level, say for set membership, one could definitely think of using the sort of accumulate and prove version of set membership, right? Where sort of the membership proof itself is outside of the main snark component, but then inside of the snark, you're proving a property. So what is it, you know, what's sort of the extent of what we want to include and things like this? Yeah.
So yeah, you can define a cryptographic protocol and say that you must achieve this effect of proving that n things are in a fixed set or a committed set, and then you can. So you may need more than the 4 levels that were in the presentation to do that, because the thing that was the top level in the presentation itself can be expanded out into various levels of detail.
But I think the first level is really for that. It's like, do it any way you like. And then sort of course, if at the end of the day, you're not using the proving system you're claiming you're benchmarking, then it's a bit not fair. But this
you
level,
kind of have to assume that people aren't trying to deliberately game the system, or that
right?
Then it's relatively easy to notice.
Mm-hmm. Right, but okay. So here's a specific example in that sense. Like if I'm claiming that I want to I don't know benchmark Groth 16 or Lego Groth 16, which just the extension. And then I'm going to prove only set membership, then it's not fair to use this accumulate and prove version because there is no property to be proven inside of the snark. So in some sense, I'm actually not using the Lego snark, the Lego Groth 16 scheme. I'm actually doing a Sigma protocol to prove membership on an RSA accumulator. Whereas if I'm actually proving a functionality that includes set membership, but it's a larger application, then actually maybe it is allowed, right? I don't know. So it's something to think about.
I think that at the topmost level, we must allow this functionality, and it is up to the implementer to describe what they actually did and how they chose to implement set membership 4,000 elements with 256 bits of security.
Yeah, and in terms of the working group, I think an immediate goal should be to really like take the most advanced version of the different costs and trade-offs, and really put that very formally. You know, take from the reference document, from the proposal, and make it even more explicit, so that already someone that's writing a paper can look at that and say, okay, this is how what I should be saying that I'm doing, and so on.
I'd like to ask briefly, switching topics, I guess, if how people, and the answer might just be no concerns at all. If anyone has concerns that by saying, here's a small set of functionalities to focus on, that there could be like negative effects, right? Like, is it clear that this would do no harm by potentially causing evaluations to overfit to something very specific? Or are people not worried about this? Because, of course, people whose proof systems will be better for other functionalities, they'll still be able to test on those functionalities, and it's not a concern.
I'm not worried, because I think protocol designers will do what they want. They won't necessarily be restricted to what's been benchmarked. If there's a good reason to use something else, they'll use something else.
And I suppose it's going to be an evolving set of benchmarks, right? So if something turns out to be really important, we would include that in the benchmarks. I guess it also depends on the type of problem that you're looking at, because I think something like arithmetic circuit satisfiability, right? That's been used in numerous research papers. That's all like the language to prove something for. And of course, you could say that's restricting you a bit. There are other things that you could also be interested in proving. But on the other hand, it's very beneficial, I think, actually to concentrate competition on one particular problem. And I think the progress you make on that problem is something that can then spill over to other types of languages. So I think there can also be an advantage to concentrate on a few important problems.
Okay, great. Yeah, just wanted to get some opinions on that. It sounds like most people aren't worried and think that the benefits, the risk isn't much, and the benefits certainly outweigh them.
I mean, I could also argue the other side, to be honest, because we are focusing a lot on hash functions, and that's partly because the existing applications used hash functions, because that was, I mean, not necessarily because that was what was efficient, but because that all of cryptography uses hash functions. So we might get into that.
Yeah, I think this point about efficiency. Yeah, I think people in an ideal world, these proof systems would scale up to arbitrary data analysis on huge data sets, and then people would be using them for much more than just pre-images of hash functions and things, but they don't right now, and that is a reason why there's so much focus on these statements.
So I mean, people used to basically think that, well, when we were designing Sprout for Zcash, we basically thought that elliptic curve cryptography was impractical to do in a circuit, and that was completely wrong. But it didn't take us long to figure it out. So I don't think that it's okay to make mistakes. It's okay to focus on things that turn out to not be the best way to do things, because it'll only take a year or two to correct that.
Mm-hmm.
I guess an interesting question is whether you can guide the efforts, right? Can you actually predict which benchmarks are going to be important 5 years from now?
No.
Well, maybe with the DARPA program, right? There's going to be a bunch of sort of incoming papers to the literature talking about all kinds of applications with very, very large statements, or at least hopefully. Not sure which are the sort of gadgets or functionalities that come out of that exactly yet, but I wanted to say though that with the example that Dara gave about having initially implemented elliptic curve cryptography in this snark and seeing it wasn't efficient, but then striving to make it more efficient, sort of actually went through this research path and innovated really interestingly, right? And it implicated a lot of, it had a lot of consequences in the whole field. I think that's an example of how maybe this idea of using the benchmarks and having the proper set of functionalities or whatnot could encourage the research and not stifle innovation, right? And right, and going back to what maybe Justin was saying, that it may be worrisome to have someone focus too much on improving a benchmark and a functionality. Well, that's exactly the example. Like if we had benchmarks back then when you created Sprout, you would have wanted to focus on elliptic curve operations anyway, right?
Right.
So that opened up a whole
we just
sort of
use whatever was, well, to start with, we used whatever was in the zero cache paper because we didn't want to change too much. But yeah.
Right. So maybe that's also sort of a question for the working group, which is, should the functionalities be sort of these high level, identifiable objects or whatnot, or should it be like, elliptic curve operation, Boolean operations? Should we go all the way down to sort of the most underlying operation?
So the problem with going too fine-grained is that it becomes not representative of higher level things. Because you're talking about so few constraints. I mean, an elliptic curve addition on a short Weierstrass or Montgomery curve is 3 R1CS constraints. That is too little to benchmark. There's micro benchmarks and there's pico benchmarks. And even if you do a million of them, then I mean,
but your standard deviation is bigger than your benchmark or something.
A million additions is not representative of any real world circuit. A multi-X that does the same number of additions is,
that's a fair point.
But that's not the same performance as a million additions.
Well, but maybe a way to do it is sort of to say, okay, I'm just the functionality is actually 10,000 additions, right? Not one, but 10,000. 10,000 operations of this and this and that.
It's still not what real applications do. A multi-X is great. Yeah, because lots of them use that.
Makes sense.
But I think we can probably just focus on the functionalities that are the most used in today's circuits. And as was previously said, we can extend the set of functionalities as people find new things, because like most of the proof systems people are using are covering like complexity classes, which are just so big, like NP, NEXP and all this stuff. We will never be able to cover them all. And we will always have an application that is going to try and do something that is not covered by the benchmark. So if the purpose of the benchmark is just to provide some indication, then it seems to me that it's just viable to target some specific statements and say, well, for this type of statements, here is the result.
I mean, I think this multi-level approach is absolutely necessary, because if you don't do that, then you will end up overfitting. And this is the only way I can think of to avoid that.
Yep, agree.
Okay, we're getting close to the end. Anybody has a last burning question or comment? Okay, it seems not. So thank you, everybody. And let's call it a close for the day. Bye.
Thank you, Jens and Abhi. Thank you to the moderators. Thanks to the note takers, Mary and Dara. You keep coming back, and it's very much appreciated.
Other people should do it as well, you know.
Okay, I'm going to stop recording.
Bye.